All right. Good morning, everyone. Can everybody hear me? Okay, great. Awesome. So today we're going to be talking about the last set of pericyclic reactions, the last type of pericyclic reactions that we're going to cover this semester, and those were the sigmatropic rearrangements. So sigmatropic rearrangements. And there's a wealth of these sigmatropic rearrangements out there in the literature. And just to limit the complexity a little bit, we are only going to focus on one specific subclass. Some could say it's the most common sigmatropic rearrangement that you'll see in organic chemistry. I just want to point out that this is not the only one. When you go up to the advanced classes, you'll encounter many more of these that have other specifics or other characteristics. But what we're going to focus on today are the 3,3 sigmatropic rearrangements. And we usually abbreviate this as 3,3 sigmatropic rearrangements. And the specific one that we're going to start talking about today is the Cope rearrangement. And that's a subclass rearrangement. And what it deals with is essentially a pi system that can form a 6-membered ring transition state. So it's usually something like this. And I'm just going to put 2 substituents on here to keep track of this a little bit. Let's just put 2 methyl groups. And what this can do is it can rearrange, let's draw it like this. And as part of this rearrangement, what happens is that we are going to break this sigma bond here, and we're going to rearrange the double bonds and form a new sigma bond at the end of this pi system. So you could think about this, if you wanted to draw the arrows, you could draw this arrow over here, this arrow over in here, and push this arrow over here. And what this gives us then is the rearrangement product, where we shifted the position of the sigma bond. So it's essentially a motion of the sigma bond along the pi system. And we still have our 2 methyl groups here that we put in place in order to account for the shift in the position. Now, these reactions usually occur only at elevated temperatures. So T, in this case, has to be usually higher than, let's say, 150 degrees or something like that. So you really have to heat them. If you look at the thermodynamics of this reaction, you see that I drew it here with a reversibility arrow. If we just count the number of bonds that we are breaking and that we are forming, here basically, if you just count the number of bonds that are involved in this, you have 2 pi bonds, 2 pi bonds, and 1 sigma bond here. And this is essentially exactly the same thing that you'll see on the other side of this equilibrium. So you have 2 pi bonds, 1 here and 1 here, and you have this new sigma bond. So enthalpically, there is not a strong driving force for this reaction to either side. 1 sigma bond. But still, in this specific case, the equilibrium lies on the side of the higher substituted double bonds. So K equilibrium lies on the side of higher substituted double bonds. So in this case, the equilibrium arrow, we could draw it out a little bit like this. That would be more accurate for this case, right? So the equilibrium lies on the side where you have a doubly substituted double bond. Another driving force that can be used to push these reactions is the release of ring strain. Let's say ring strain as a driving force. And there's a couple of examples where you essentially create a ring expansion using this 3,3 sigmatropic rearrangement. can say, for example, if you have like a 3-membered ring here, the ring strain stored in this 3-membered ring drives the reaction to the ring open species. And again, we could draw here the arrows. And you turn this into a 7-membered ring. Let's see here. Something like this, and the double bonds are over here. And the driving force in this case is release of ring strain. Release of ring strain drives the reaction towards the ring opened product, this the 7-membered ring. There is one last type. So the Cope, just to maybe to generalize this a little bit, the Cope rearrangement usually deals with these all carbon systems where you have essentially a linear structure with 2 double bonds at the ends and that are linked in the middle by a sigma bond. So that's classically the structure that we define as the Cope rearrangement. There is some heteroatom structures that we just want to introduce in the subsection here, and we call these, in this case, for example, if there's an oxygen is involved, we call this the oxycope. Oxy basically for oxygen. And this is a reaction that you see quite commonly, and it's quite useful. The only difference with respect to the traditional Cope is that in this time, you have a substituent on here that is an alcohol, for example. And you can imagine that these are relatively easily made. If you think about this, this comes directly from, for example, an aldehyde plus a vinylic Grignard reagent. So MgBr. So if you react these together, for example, you directly get the species. So they're easily accessible. And if you do the rearrangement on these structures, again, we can draw the arrows. You quickly realize that the intermediate that you generate is an enol. So let's draw this out here. Double bond here, and then you have this enol functional group here. And of course, the equilibrium lies a little bit more on the side of this one because this is the higher substituted double bond system. But ultimately, what pushes this equilibrium totally to the side of the rearranged product is the tautomerization that you can induce. It forms the aldehyde from this enol. So you can draw out here O. And this is tautomerization. So this proton transfer, this tautomerization here essentially is responsible for the driving force of this reaction. So you can say driving force is the tautomerization. And this equilibrium lies far on the side of these products. Now, but in order to understand this a little bit better and understand this concept of the 3,3 sigmatropic rearrangement, what we are going to look a little bit closer at is again the molecular orbital analysis of this. And if you take a quick look at the prototypical Cope rearrangement, so let's say frontier molecular orbital analysis, FMO analysis. What we're dealing with here is essentially a rearrangement that involves 2 allylic radicals. So during the rearrangement, this has to go through some form of a transition state where I start breaking this bond here. and I'm starting to form this new bond on the other end of the pi system. So you could think about this as going through a transition state that looks a little bit like this, where you have two allyl radicals essentially weakly interacting with each other. And I'm just going to denote this essentially with these dotted lines. So this would be the delocalized pi system, and the new sigma bonds that we are forming in this case. So formally, you could think about this also as something, yeah, let's draw it out like this. So you could think about this as an allyl radical and another delocalized allyl radical in the transition state. Right. So the analogy or the similarity to the classical, what we know as the allyl radical, is pretty evident if you assume a transition state like this, and that leads essentially to the explanation for this reaction based on frontier molecular orbital analysis. If you just assume that both of these fragments, as part of this mechanism, go through essentially an allyl radical stage. Or an allyl radical type transition state. So if we look at the molecular orbitals that would be involved in this, we can again draw our allyl system out. So this is now 3p orbitals. And we know that the second one has a node in the center, and the highest one has two nodes. So this way, this way, this way. Okay, this is 5, 3, 2, and 1. And if we think about these as the allyl radicals, and we associate the energy levels with this, and we start populating this with electrons, we know that phi1 is going to have 2 electrons, and we have a total of 3 electrons in the system, so this is a single occupied molecular orbital. So remember from the photochemical reactions, we called this a SOMO, a single occupied molecular orbital. So these are essentially the orbitals, the highest occupied orbitals that are involved in this reaction. And if we were to kind of draw a transition state that resembles basically this or this structure here, we can easily design this based on this SOMO. So I'm just going to, let's say, transition state model for 3,3 sigmatropic rearrangement. Then you can basically just go ahead and draw 2 allyl radicals So there's a node here, of course, and then we can draw the other one. Let's see, below here. And there's a node over here. And now we can pick up the shading that we analyzed from our molecular orbital diagram. So the lobes are shaded on opposite sides, and we can build a matching structure essentially down here. And if you take a closer look as part of this, now you see that both of these segments react as the SOMO. And you see a favorable overlap between these unshaded lobes and between these shaded lobes at the ends of the pi system. So that would indicate that if you perform this reaction, it would proceed through something like a chair type transition state, where each of these fragments essentially reacts as the single occupied molecular orbital of an allyl radical. So you can say here suggests chair transition state. Now, we can check this experimentally if these reactions actually proceed through a chair-like transition state by just following the stereochemistry at these ends of the pi system here. So if it goes through a chair-like transition state, there should be one specific confirmation how these substituents end up in the rearrangement product. And this is something we can do simply with a small molecule. So let's say we have something like this. So that's 1, 2, 3, 4, 5, 6. Yeah, and we induce a thermal rearrangement in this structure. So let's say we heat this. So let's say 200 degrees Celsius here, and we expect it to rearrange at least to a certain a certain fraction to this product here. Right? Now, one thing that you immediately see is that I have not defined the stereochemistry of these methyl groups here, because they are set essentially by whether these bonds here are cis or these bonds are trans. Now, in order to figure this out, the best way to do this is kind of to redraw this structure already in form of a six-membered ring transition state. So if we start out with methyl, so this goes down, and then double bond, methyl like this. Now the six-membered ring is a little bit easier to see. So we have, let's say, this is the bond that's being broken. So we have 1, 2, 3, one allyl fragment, and we have 1', 2', 3' over here. So this is our six-membered ring, and this is the new bond that we are essentially forming, while this is the bond that we are breaking in this process. Now, if this comes together in a six-membered ring transition state, we can draw this out. Let's say, and then let's do this as like a dotted line, because this is kind of broken already at this stage. And then down, down, methyl, methyl, and we can add the extended pi system and the new bond that is forming as part of this. So this would be essentially our six-membered ring transition state. And if we follow this through, I should have drawn this as an equilibrium arrow here. Then we basically get the rearrangement product out of this. And of course, this is also still a six-membered ring transition state. So we can draw it like this. Let's make this a little bit longer. And then down and up again here. And this methyl group here points out equatorially, and this methyl group here points out equatorial too. So if we translate this then into a planar structure, both of these are equatorial. Then we can define what the stereochemistry, the induced stereochemistry around these two carbon atoms is going to be. In this case, this methyl group is going to point downwards, and this methyl group here is going to point out of the plane of the board. So based on that, we can then conclude, if this is our major product, we can conclude that the transition state, or the reaction, has to go through a transition state that adopts this favored six-membered ring, where you place these methyl groups in the quasi-equatorial positions to reduce the strain on the ring system. So the stereochemistry for these reactions is essentially defined by the favorable conformation of the six-membered ring transition state. And they're the same rules that we had many times in six-membered rings. The large substituents should be in an equatorial position. So large R in equatorial, position. All right, so now these carbon-based rearrangements, these carbon-based 3,3 sigmatropic rearrangements are not the only ones that are out there in the literature. There is alternatives that, that also include heteroatoms along this backbone of the rearranging structure. And one that is quite common is the Claisen rearrangement, which basically introduces or swaps out one of the carbon atoms along the backbone for an oxygen atom. So that's the second most common rearrangement among the sigmatropic 3,3 rearrangements. So the Claisen rearrangement. So as I said already, this includes an oxygen atom now. So a classical structure would look something like this, where you have an oxygen or an ether in this case. And you still have retained essentially the rest of this pi system that we have been talking about previously. You can again introduce our numbering 1, 2, 3, and 1 prime, 2 prime, 3 prime. And this means that basically what we do during the rearrangement is we are forming this sigma bond and we are breaking this sigma bond here. So in this case, the driving force for this reaction lies strongly on the side of the rearranged products, for the simple reason that you're basically breaking an ether carbon oxygen sigma bond, and in the product you're forming a carbon oxygen double bond. So thermodynamically, this favors the formation of the product. So the rearranged product then is going to look something like this. So this forms an aldehyde. So we can do a quick thermodynamic analysis for the bonds that are broken and the bonds that are formed in this case. So if we say here bonds broken, and let's say bonds formed. So as part of this rearrangement here, we are essentially breaking a carbon-oxygen bond, so the CO bond here, and we are breaking basically the carbon-carbon pi bonds. So let's say pi bonds here. And this is the sigma bond. And on this side, what we are essentially forming is a new carbon-carbon sigma bond, so this bond here. And what we are breaking is, and the other part that we are forming is essentially the carbon-oxygen and a carbon-carbon bond. So we form a carbon-carbon pi bond, and we form a carbon-oxygen pi bond, right? And if we just crunch the numbers here, roughly a ballpark in kilocalories per mole, this one is about 85 kilocalories per mole. Each of these two pi bonds is about 65 kilocalories per mole. This carbon-carbon bond here, let me see, what is it? It's about 85. And then the CO bond here, the CO pi bond is 85 kilocalories per mole. And we had here the carbon-carbon pi bond as 65 already. So ballpark is that the driving force for forming the rearranged product here is a net gain in bond energy of around 20 kilocal per mole that I lower the energy in the system. So the driving force lies far on the side of the rearranged product. And this chemistry can be used quite efficiently to easily access unsaturated structures that have like a carbonyl, for example, or a ketone, and a double bond at opposite ends of the pi system. And one most famous of these these reactions is the Johnson orthoester synthesis. So Johnson orthoester synthesis. And you'll very quickly realize that oftentimes these sigmatropic rearrangements are somewhere hidden along the mechanism, and they allow the introduction of high degrees of complexity from very simple starting materials. So I'm just going to show you the reaction first. So you usually start with an allylic alcohol, and then you treat this with an orthoester. So that's basically just the acetal of an acetic acid, or an ester in this case. So let's say, so it's 3 ethoxys essentially that are attached to this carbon atom, and you can easily make this from an ester by just forming the acetal from that carbonyl essentially, and then you basically just have to heat this with a little bit of an acid, and what you get out of it is maybe something that you don't immediately expect. You get the ethyl ester out of this system. So we're going to go through the mechanism in a lot more detail just to clarify like how this works. So, and where essentially the 3,3 sigmatropic rearrangement occurs. Now, the first step of this reaction obviously is the activation of this orthoester by the acid. So we can quickly draw this out. This is chemistry that we have seen many times as part of the first third of our semester. So OET, 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 and if I have a proton here, a lone pair from this oxygen can attack this proton, and we get an activated species. That's just a very simple protonation, and I can draw this out. Positive charge over here. And then as part of this, this is now a pretty good leaving group. This can grab the electrons essentially and be removed from the system, be cleaved from the system. And to stabilize this carbocation that is forming, we can push the electrons in from one of these oxygens to form essentially an activated carbonyl. And you'll recognize this very quickly as an activated form of an ester. So if we do OET here, now it's a positive charge here, and we have another ethyl group here. And this is now basically our activated electrophile that can be attacked by our alcohol, which is the unactivated nucleophile in this case, right? So the alcohol there is not a fantastic nucleophile, so that's why we need this, this activation. And you can draw the arrow the same way, attack on a carbonyl and forming a tetrahedral intermediate, as we have done many times before. So all of these are, of course, still equilibrium reactions, and what we get out of it. So let's draw this. Let's draw this already in the conformation that we need for the rearrangement. That makes it a little bit easier. So we have the positive charge here, and then we have one ethyl group here and one ethyl group going to the back. Now you can easily imagine that there's going to be a proton transfer mediated by the solvent, where this proton is essentially transferred to either of these oxygens, making them a good leaving group. So proton transfer step here, and I'm just going to draw this out again. Now as the proton transferred species, let's say the one in the front is now the protonated form, and the one in the back is still the unprotonated species. So this has now a positive charge here. And you can easily imagine that this will rearrange again. This is a good leaving group, is being kicked out, and these electrons as lone pairs on the oxygen move in and form a new carbonyl. So again, you lose one equivalent of ethanol, and you form again this activated activated ketone. Now, I'm just going to move this up a little bit so I have a little bit more space. Hope you can still see this. Okay, so from here there is a simple tautomerization. You can lose a proton here. So let's say just the solvent, for example, can abstract this proton. These electrons push in and form the enol, and this pushes out here. So you end up with an enol ether in this case. So, and that's basically now our system completely set up for the 3,3 sigmatropic rearrangement that we were aiming for. So, OET. Now, here is where you basically realize that you're dealing with a 3,3 sigmatropic rearrangement. You can again use your numbering 1, 2, 3. These are the carbon atoms or the atoms that are shifting. And here you have 1 prime, 2 prime, 3 prime. So this is the bond that you're breaking, and this is the new bond that you're forming as part of this rearrangement. And we can push the electrons around again. So maybe let's pick a different color here to make it clearer. So let's say we can take these electrons and push them in here. We can take these electrons, push them into this bond, and move those over to this side. Now we have just three sigmatropic rearrangement, and the product of this is then going to be draw the O here, and the ethyl group on this side. And this basically, if you remember what our expected product was going to be, is essentially identical to the ester that we had drawn right up here at the top of the reaction. So this basically is exactly the same product as this one that we had drawn over here. And the key step for all those reactions is essentially the activation of the orthoester with the acid, the attack of the allylic alcohol that leads to the setup for the 3,3 sigmatropic rearrangement that you see down here. So the double bond of the enol ether here, and this allylic double bond that you have on the other side of the system. After the rearrangement, you're left with the ester on one side and the double bond on the other side of the pi system. Now, this is just one example for the easy access to complexity that all these 3,3 sigmatropic rearrangements can give you. I just want to introduce two more of these that are quite common in organic chemistry. One of them leads to nitrogen heterocycles, and it's a combination of two reactions. One is an ASA Cope reaction, followed by something that we have seen in the first part of our lecture in 12b, and this is a Manish reaction. So it's now a combination of a rearrangement, a 3,3 sigmatropic rearrangement followed by a Manish reaction. And you'll quickly see like how fast you can build up complex structures using this cascade of reactions. So let's start out with something that looks like this. you have an amine and an allylic alcohol, and you just react this, for example, with an aldehyde. And we keep this generic here, we just put an R on here. And if you stir this together under somewhat acidic conditions, you end up with a nitrogen heterocycle, 5-membered ring heterocycle with an R group over here and an aldehyde functional group on this side. Now, it is not immediately obvious how you get from this starting material to this product. But if you look at the title of this reaction, Azacope followed by a Manish reaction, most of you can probably wiggle your way around this and figure out how this proceeds. So if we have to do an Azacope first, what we need to do is set up this pi system, this characteristic pi system, in order to do the 3,3 sigmatropic rearrangement. This by itself, this building block, only has one part of the pi system. So you could say that's numbering 1, 2, 3. And over here you have 1 prime, 2 prime, but your 3 prime is missing, right? And this is basically brought in by this aldehyde. And you can think about this easily under acidic conditions. This is just an imine condensation here. It's the first step. So mechanism. So the first part of this step is essentially an imine condensation of the primary amine with the activated aldehyde. And I'm not going to go into all the details of these steps. We have done imine condensations many times. I'm just going to draw directly the expected product from that. So that's going to be then the OH, the iminium ion, positive charge here, and then R out here. And within one step, you already have generated something that gives you the chemistry or the rearrangement of functional groups that you need for the sigmatropic rearrangement. Again, we have our 3 carbon atoms on this side, and down here we have 1 prime. The nitrogen is essentially 2 prime, and this carbon atom that we brought in from the aldehyde is 3 prime. So now we know that we can form this bond here, and we can break this bond here in the 3,3 sigmatropic rearrangement. So this is basically the classical 3,3 sigmatropic rearrangement, with the only difference that now you have a nitrogen atom here instead of a carbon atom, but mechanistically that's exactly the same thing. So if we take the arrows again and we start pushing those around, so let's say we can push this one in here, can push this one over here, and push this one over there, then we end up with an intermediate that resembles this rearranged species. We have nitrogen here again, positive charge. We have the residue R here. And then over here, we have our OH. And from here, what you can quickly realize is this is basically set up already perfectly for the second part, which is essentially the Manish reaction. You have an enol here that is nucleophilic at this position, and you have an activated electrophile here in this iminium ion. And now if you just take the arrows and push them around from here into here, from here, these electrons, we push them over here, and we can take these electrons and push them back to the nitrogen. You see that you're forming a 5-membered ring, 1, 2, 3, 4, 5, and this basically here rearranges to an aldehyde. So this is then basically your Manish reaction, and you get the 5-membered ring product out that we had here up at the starting material. So oftentimes these sigmatropic rearrangements are not immediately visible if you look just at your starting materials. Oftentimes the setup that allows the 3,3 sigmatropic rearrangement is formed somewhere along the reaction, and you basically have to build this up first before you can do the rearrangement. All right, so the last one that I want to talk about is a heterocycle synthesis that also uses these 3,3 sigmatropic rearrangements, and it's called the Fischer-Indol synthesis. And what this essentially does, it builds up an indole from two very simple building blocks. So on one side, you need a ketone, and on the other side, you need something like an aryl hydrazone, or an aryl hydrazone is the most common species that you use here. So you have something like this, and H2. So, and you bring these together under an acid catalysis, H+, again, and what it forms is your indole heterocycle. So 5-membered ring here, NH, and then depending on what your ketone was, in this case, it is a 6-membered ring, is fused essentially to this side here. There's a double bond missing. Okay, so basically it takes a ketone, hydrazone, and makes an indole out of this. Now, obviously, if you just have a glance at these real quick, it's really hard to see where the connection in the synthesis is to the 3,3 sigmatropic rearrangements. And it looks again like something where we have to build up the structure, the core structure of these 6 atoms in a line with the 2 double bonds at the end that are so characteristic for the 3,3 sigmatropic rearrangement. Now, obviously, if you just look at this ketone and this hydrazone and think about how they could react under acidic conditions, I think all of you very quickly realize that this is basically just a reaction of the lone pair on this nitrogen with a carbonyl, the same way we have seen the reaction of hydrazines with carbonyls in, for example, the Wolff-Kishner reaction. So this first step is pretty simple. So this is essentially just a condensation reaction. So if I take the ketone and react it with the hydrazone, I get a hydrazone. So NH, and then the ketone reacted and condensed here under extrusion of water, and that's our hydrazone. And essentially that's the same structure. If we left out basically this phenyl ring, it would be the same building block that we made as part of the Wolff-Kishner, the first step in the Wolff-Kishner reaction, right? Now, what this can do is a tautomerization. So this is still kind of an imine here, and we know that these hydrogens at these positions here can be activated and can be acidic. So this would be, the first step would be here tautomerization. So again, we then form, this is nitrogen here, an enamine essentially. And if you pay close attention, you already see now the starting point for the 3,3 sigmatropic rearrangement. Because if you do the counting here, you can say like 1, this is our nitrogen atom 1, This is our carbon atom 2, and this is our carbon atom 3 here in at the edge of this pi system. And on this side, you have 1 prime. You have down here, let's say 2 prime here, and we have 3 prime here on this side. So again, the new bond that we're forming is the one between 3 and 3 prime, and the one bond that we are breaking is the one between 1 and 1 prime. So the next step for this is essentially the 3,3 sigmatropic rearrangement. And you end up with a structure that's kind of a very short-lived intermediate, where you broke the aromaticity of this ring, and we can push the electrons actually, so it makes it a little bit easier to see. So we have then the nitrogen here, and we have still a hydrogen attached to that. Then we have a bond coming out here. We have our 6-membered ring. And then on the other side, again, we have N and H over here. Now, it's pretty obvious to all of you that this is not going to be a particularly happy system here. So this will very quickly re-aromatize, and I'm just going to intentionally draw the arrows like this because the driving force pushes this essentially very quickly towards the re-aromatization. So you form essentially an aniline, and this is, you can think about this simply as a proton transfer from this position, or a tautomerization from this proton over here, pushing these electrons back here, and these electrons back out to the nitrogen. So you can quickly get back to your aniline. So NH2 here, and you still have this imine species attached down here, NH. So this is a much happier species than this, and here basically you're set up already to just do a polar reaction where you can take the lone pair on this nitrogen and attack this as the nucleophile, on this fragment here as the electrophile. So I can push the electrons out like this, and you end up with let's see. How should we draw this? 6-membered ring, and then we still have NH2 here, a hydrogen, and the 6-membered ring here, and you're still left with 1 hydrogen at this position. Under acidic conditions, you can further protonate this and make this a better leaving group. So H plus can come in here, and that basically, well, let's give us a little bit more space. Let's redraw this. And NH3 plus. Now this is a pretty good leaving group, or we made it a pretty good leaving group. We can kick this out and basically do an elimination here that leads to the last double bond that you need for your indole. NH. And then your 6-membered ring. And that's basically the indole structure that we had at the beginning. Now, the nice thing is that this synthesis, if you look closer, the key step is essentially this 3,3 sigmatropic rearrangement, and all you need in order to make this work is basically a fragment or a carbonyl that has one enolizable alpha position here. So this is kind of like the key fragment that you need here in order to form this enamine here that allows the 3,3 sigmatropic rearrangement. So anytime you have a hydrazone reacting with a ketone or an aldehyde or anything like that, that has an enolizable position, you can access this, this structure that induces a 3,3 sigmatropic rearrangement, and that sets you up on the pathway all the way to the indole down here. All right, so this was essentially the last part of this section that we wanted to talk about pericyclic reactions. I'll close this chapter here. There is plenty of problem sets that we gave you to practice this a little bit. I saw that there's a ton of questions in the chat. I can't go over all of them. If you have specific questions, then come to my office hours right after that, and I can answer them. There. It would take me too long to kind of go through this step by step right now. Now we still have a couple of minutes, so I'd like to start a little bit into the last chapter here. This is chapter 25, and it deals with this last type of reactions that I announced that we will be talking about, and these are kind of the radical reactions. So remember, when we most of the semester we have been talking about polar reactions, where you always had a nucleophile and an electrophile reacting with each other. Those were accounting for about 90% of all organic chemistry. Then we had the pericyclic reactions, and this is the chapter that we just finished, where we had the cycloadditions, the electrocyclizations, the cheletropic reactions, and the sigmatropic rearrangements. And the last part that I mentioned, or the last type of reactivity that I mentioned at the beginning of the semester, the radical reactions. And you'll find these in your book in chapter 25. So chapter 25, reactions involving radicals. And this is something that is a little bit different from what we have looked at so far. Previously, all the reactions that we have been looking at, we have been able to draw these classical 2 electron arrows when we are pushing electrons around. So we always assumed that 2 electrons move here at the same time. For radical reactions, we only assume that 1 electron moves at a time, and we have a little bit different nomenclature for this. We use these fishhook arrows that basically are not a full arrow at the end, but only basically half an arrow. So this means that basically 1 electron is being moved around in these systems. Now, a classical example for these radical reactions, they always, or most of the time, they involve some form of a free radical species. So a simple example how to generate a radical is the homolysis of the bromine-bromine bond. So if you have a bromine molecule, let's kind of draw in all the electrons for once. This bond here is relatively weak, and if you heat this up, the temperature can supply enough energy that this bond actually breaks, and that you get basically a split of this bond, a homolytic split, where you end up essentially with 2 bromine radicals. So these are free radicals now. And of course, they don't have an electron octet. So they tend to be very reactive species. And that's something that is very characteristic for radical chemistry. Now, of course, this is not only restricted to simple heteroatom bonds, but you can also generate radicals on carbon structures. And since we're in organic chemistry, we're mostly interested in those. So if you have, for example, a methylene group, you can do a similar reaction. I'm not going to talk about the details now, how you can induce this, but formally you can also draw these radical arrows where one of the electrons essentially of this bond moves away with the hydrogen and the other one remains attached to the carbon atom. So that leaves you basically with a hydrogen atom. This is a free radical, plus then in this case, carbon-centered radical. So the electron that was one electron that was in this carbon-hydrogen bond remains with this carbon atom. Now, the critical factor to consider for these radical reactions is essentially the bond dissociation energy. So the energy that it takes to cleave this bond homolytically and to move one electron with one fragment and have the other electron remain with the other fragment. And there's a nice picture for this that you've seen many times already. And this is kind of like the classical Lennard-Jones potential for a bond. So let's say this is distance r here, and this is let's say just the delta energy. So classically, you think about this as, so this is 0 point, let's say one atom sits at this position. And as you move in basically an atom, you basically form, or you lower the energy when you get to the bonding distance before the energy rises again, where you get the repulsion of the nuclei. So the classical Lennard-Jones potential looks something like this. So here you have the bonding distance, and then you have a slow increase in energy again until you have the infinite separation. So this is essentially here, let's take this for the example of the Br molecule. So this would be essentially the bonding distance. And here you would basically have an infinite separation between the two nuclei. And the actual bond dissociation energy corresponds to the energy that you have to overcome in order to get from this, this bonding distance. So let's say call this bonding distance to this infinite separation. So essentially, you're dealing with the energy that corresponds to this delta here. So let's call this delta E for the Br bond. And usually this is defined essentially as the bond dissociation energy. So this we call usually bond dissociation energy. And this is usually abbreviated as BDE. Now, in this case, if we talk about the bromine molecule, the BDE for bromine is roughly 45 kilocalories per mole. So if you think about activation barriers or something like that, that are usually in the range of like 10 to 20 kilocalories per mole for the polar reactions, 45 kilocalories per mole is a substantial amount of energy that you have to pump into a system in order to make this bond break homolytically. So where basically one electron stays with one bromine and the other electron stays with the other one. Now, in your textbook, you have an exhaustive table of bond dissociation energies. So I'm not going to repeat this. You can basically look this up. But there is kind of a general trend that I just want to kind of discuss here a little bit that you should roughly keep in mind. So let's call this some general bond dissociation energies that you should have in the back of your mind in order to analyze some of these reactions. So the ones that we are most interested in organic chemistry are the ones that relate to the carbon-hydrogen bond, because that's usually the bond that is getting activated in our system. And if we just, let's see, let's make a table here. And all these energies that I'm going to display here are going to be in kilocal per mole. So that's the unit. So if we talk about simple alkanes, so simple saturated alkanes, the bond dissociation energy for the CH bond is usually around, let's say, 90 to 100 kilocalories per mole. That's just ballpark. This is averaged over many structures. If you can facilitate this bond dissociation if you allow the system to stabilize essentially the free radical intermediates. So if you, for example, have an allyl system, so this CH bond here, for example, is significantly weaker because the resulting radical, allyl radical, essentially is stabilized through the resonance here. So this drops the bond dissociation energy by a little bit. So this is roughly 85 kilocalories per mole. But pi systems generally are not really assisting this bond dissociation. So if you have a vinyl radical, for example, or if you have Papardjo radical, so these bonds, these CH bonds are actually significantly stronger. So this is roughly 111 kilocalories per mole. And this Papardjo one is actually 133 kilocalories per mole. So these are really strong bonds here. Okay. All right, let's move on to heteroatom bonds. So if we have, for example, C bonded to a heteroatom X, the classical, just as a reference, a CC bond is roughly around 90 kilocalories per mole. If you have a CF bond, that's a stronger bond. That's around 100. I think in the textbook it's about 108. And a CI bond, that is a weaker bond actually. That's about just 56 kilocalories per mole. So this basically gives you a range of possible fragmentations that are easier than other ones. So a CI bond, for example, is easier to cleave than a CF bond and a CC bond. Now, let's see, a couple of other bonds that you see quite commonly. Let's say, let's hydrogen X bonds. Let's do those. So for example, a classical one is the OH bond in water. That's a pretty strong bond, so roughly 119 kilocalories per mole. If you have a methyl alcohol, or methanol, H3CO, this is a little bit weaker. This is around 103 or 102 kilocalories per mole. And then lastly, let's just talk about the heteroatom bonds. So the most typical ones that you'll see in radical chemistry are going to be the ones, for example, where two bromine atoms. So the bromine molecule, for example, and we said here, what did we say in the previous slide here? It's around 45 kilocalories per mole. And then the iodine-iodine bond is even weaker. It's basically just 36 kilocalories per mole, right? So it gives you kind of a ballpark of the bond dissociation energies that you're going to be dealing with. The weakest ones in this entire table are obviously the ones that include halogen atoms. So you'll see a lot of this of these halogen-derived chemistry as part of these radical reactions. Yeah, I think that's a good point to stop for today. We'll talk about the structure and the stability of the free alkyl radicals at the beginning of next class, before we actually move into the typical elementary steps that are involved in these radical reactions, and how you can daisy chain these elementary radical reaction steps to form cascades or chain reactions of radicals that form, for example, that are used, for example, in large industrial scale halogenation processes. Chlorination, bromination processes usually go via these radical reactions. Okay, so I'll see you on Thursday, where we're going to continue with this, and we'll have plenty of time to finish this last chapter by next Tuesday. So we are pretty much like about half a lecture ahead of our schedule. Okay, so I'll compile this lecture and I post it, and I'll be in my office hours at 9:30. Okay, see you on Thursday.